We put telescopes in space to see what Earth won't let us see. Its atmosphere blocks and distorts infrared light, the light that carries information from the earliest galaxies. To see the universe clearly, we had to leave Earth behind. That's where Hubble and James Webb Space Telescopes comes in. Unlike Hubble, which mostly observes visible light, Webb was designed to observe infrared. Infrared light comes from the earliest galaxies, light stretched by the expansion of the universe and hidden behind clouds of cosmic dust. To detect that faint infrared signal, Webb had to be completely different. And it had to be large, much larger than Hubble. Webb's primary mirror is 6.6 meters wide. Hubble's is just 2.4 meters. That means Webb collects more than 6 times as much light. For scale, if a human stood next to Webb's mirror, they would barely reach the height of a single segment. The mirror is made of 18 hexagonal pieces, carefully arranged into a single surface and coated with a thin layer of gold. Not for appearance, gold reflects infrared light better than almost any other material. Together, these mirrors allow Webb to detect incredibly faint signals, light that has been traveling for over 13 billion years. But a mirror this large cannot fit inside any rocket, so Webb was designed to fold. At launch, the telescope was packed tightly inside the rocket fairing, folded like a piece of precision-engineered origami. After launch, Webb had to unfold itself in space. The Sunshield deployed. The secondary mirror swung into place, each mirror segment unfolded and locked. More than 300 single-point failure steps had to work perfectly, automatically million kilometers from Earth. There was no manual control, there was no backup telescope, and then Webb traveled even farther. It does not orbit Earth like Hubble. Instead, it orbits a location called Lagrange Point 2, about 1.5 million kilometers away. At this distance, the Sun, Earth, and Moon always remain on the same side of the telescope. This allows Webb's massive sunshield to block their heat and light continuously, because infrared telescopes must stay extremely cold. Any heat from the telescope itself would glow in infrared and overwhelm the faint signals from space. Webb's 5-layer sunshield is roughly the size of a tennis court. Each layer radiates heat outward, step by step, so that by the time heat reaches the telescope, almost none remains. As a result, Webb cools to about -233 degrees Celsius, colder than most natural objects in space. This extreme cold is what allows Webb to see faint heat from distant galaxies, newborn stars, and the atmospheres of alien worlds. Behind the Sunshield sits the Spacecraft Bus. This is Webb's control center. It houses the power systems, computers, communications antennas, propulsion, and thermal controls. While the telescope focuses entirely on collecting light, the Spacecraft Bus keeps Webb alive, stable, and connected to Earth. To point accurately, Webb must always know exactly where it is. That's where the star trackers come in. They continuously identify known star patterns and calculate Webb's precise orientation in space. This allows the telescope to lock onto distant targets with incredible stability, even while orbiting a point far beyond the Moon. When light finally enters the telescope, Webb doesn't just turn it into pictures. It is sent through a system of scientific instruments, each designed to extract different kinds of information from the same light. The 3 main instruments are NIRCam, NIRSpec, and MIRI. Together, they allow Webb to image the universe analyze its chemistry, and detect faint heat from the coldest and most distant objects ever observed. NIRCam is Webb's primary camera. It captures high-resolution infrared images and is also responsible for keeping the telescope perfectly focused. During commissioning, NIRCam was used to align all 18 mirror segments into a single, precise optical surface. In science mode, NIRCam images distant galaxies, star-forming regions, and exoplanet systems, revealing structures hidden behind cosmic dust. NIRSpec goes a step further. Instead of just imaging light, it splits it into a detailed spectrum. This separates incoming light into thousands of precise wavelengths. Each wavelength carries chemical information. From this, scientists can identify elements and molecules, measure temperatures, and determine how fast objects are moving, even across billions of light years. MIRI works at even longer wavelengths. It observes mid-infrared light, which corresponds to heat. MIRI can detect the faint thermal glow of cold objects, forming planets, dusty disks, and extremely distant galaxies. These wavelengths are completely invisible to Hubble. They allow Webb to see through thick clouds of dust and study regions where stars and planets are actively forming. Together, these instruments don't just observe the universe, they decode it. This is how Webb can detect water vapor, carbon dioxide, and methane in the atmospheres of distant exoplanets. Compared to Hubble, Webb sees deep into dusty regions where stars and planets form. Compared to WISE, Webb provides far greater resolution and sensitivity. Where WISE sees broad infrared shapes, Webb reveals structure and detail. Where Hubble sees dark clouds, Webb sees stars forming inside them. These telescopes don't replace one another. They work together, revealing the universe across different wavelengths of light. The upcoming Roman Space Telescope will survey huge regions of the sky. Webb does the opposite. It zooms in. Roman will find targets. Webb will study them in extraordinary detail. Unlike Hubble, Webb cannot be repaired. It is simply too far away. That's why every system was tested for years before launch. Webb was built to operate for at least a decade, and possibly much longer. Webb has observed some of the earliest galaxies ever seen, mapped star-forming regions hidden inside cosmic dust, detected complex molecules in distant atmospheres, and watched galaxies forming just a few 100 million years after the Big Bang. It is not just showing us the universe, it is rewriting its history. Hubble showed us where we are. James Webb is showing us where we came from. And for the first time in human history, we are watching the universe build itself. Thank you for watching.